How A to zero may explain dark matter, a really new idea for astrophysics. Gravity is universal. That means that anything, even objects without mass, photons, experience gravity. Therefore, gravity is best described as the one field which underlies everything. Gravity is described by the curvature of space and time, the curvature of the background of the universe. Gravity is not a force, but comes from time running slower and space being more compact in the vicinity of massive objects. The equations that describe how to calculate the curvature of space and time out of the distribution of mass and energy are Einstein's field equations shown below. The left-hand side, the Ricci tensor and the metric, characterizes the curvature of space and time. The right-hand side, the energy-momentum tensor, represents the distribution of mass and energy. The metric is what describes the curvature of space and time by describing how we measure distances. The general spherically symmetric form of a metric is this, where A is the coefficient of space and B is the coefficient of time. Using Einstein's field equations for a given mass distribution, the metric can be derived. For example, the famous Schwarzschild metric. The Schwarzschild metric can be derived directly without further assumptions from the field equations. In Wikipedia is written how. In the Schwarzschild metric, the coefficient of the space part of the metric is larger than 1. That means that near the central mass there is more space than further away from the central mass. The space is more compact in the vicinity of the central mass. Additional space is pressed into the existing 1. However, and that is important, A approximates 1 in the infinity. Einstein's field equations directly lead to the Schwarzschild solution and therefore directly lead to A to 1. They are the mathematical synonym for the statement mass curves the space and the space is otherwise flat. The Schwarzschild metric can be derived directly from the field equations. In a previous film, I speculated that probably A to zero can be derived from Einstein's field equations. That was a mistake by me. It cannot. From the Schwarzschild metric, Newton's law can be derived, which is well confirmed within the solar system. At larger scales, however, there is a deviation from Newton's law. We measure higher velocities than expected, for example, in the rotation curves of the galaxies. To save Newton's law for galaxies, two approaches are made, both changing something in the field equations. Either new particles are postulated which add to the existing mass on the right-hand side and are not visible, dark matter, or new fields are postulated which add on the left-hand side. However, if we add something on the left or on the right, the general structure of the field equations doesn't change. Even with those fields or with the dark matter added, and by the way, even after calculating it in 26 dimensions as in string theory, there is always a background space. There is always A to 1. I want to raise the question whether it could be possible to find other underlying field equations which lead to A to zero. The meaning of those field equations should be something like space surrounds mass like a field, and the mathematical form something like the divergence of space equals mass. With A to zero, gravity would appear to be stronger for galaxies. That is exactly what we measure as the dark matter effect. By expanding relativity theory with the A to zero idea, there are two cases between which we have to distinguish. primary gravitation, which applies for galaxies, and secondary gravitation, which applies for solar systems within the background of a huge galaxy. The effect that we do not experience primary gravitation within the solar system is that of large magnitude differences. A lake on the surface of the Earth appears to be flat and doesn't reveal the curvature of the Earth as a whole. That's all for today. Thank you for your attention.